Our seminar. Today we have as a speaker Adolfo del Campo from the University of Luxembourg. Let me introduce Adolfo. He studied in the Basque Country at the University of the Basque Country and also did his PhD there. Then he did several postdocs in Ulm, Hanover, MIT, and Los Alamos before he came or went back to the Basque Country as an ICA Basque professor. And since about 1 year, he's full professor at the University of Luxembourg, where he's working on essentially quantum dynamics, just some keywords: quantum control, adiabatic control, adiabatic quantum computation, phase transitions, open quantum systems, and also quantum thermodynamics. And lately, he's also interested in topology, and this will be the topic of today's talk. He will speak about probing topological defect formation in a quantum annealer. Welcome, Adolfo, to our virtual seminar. Just before we start, one remark. Probably most of you already know it. If you have questions, just write it to the chat or raise your hand. So, Adolfo, thanks for accepting our invitation, and the stage is yours.
Well, thank you very much for the invitation. Yeah, so it's a pleasure to be here. So today's talk is going to be about recent progress in using quantum annealers as a test bed for non-equilibrium statistical mechanics, and in particular, some paradigms to study topological defect formation. So let me just, let's see where I can pass the slide easily. So this I should have tried before, and now I cannot pass the slide. Oh, here we are. Yeah, excellent. So, just a quick picture of the to show the current group now in Luxembourg. So it's Jing Yang, a postdoc, and 3 PhD students. And I work closely as well with a group of Aurelia Chenou, is so-called quantum dynamics, quantum control and dynamics group. And as Sigmund said, just to give a bit of an idea, we not only do the part of quantum annealing, which I will cover in this talk, but also works on quantum control, on information geometry and quantum metrology, and other parts which maybe are closer to math, such as integrable systems and strongly correlated systems and so on. But today's talk is going to be focused on the use of quantum annealers in the connection of their use to probe dynamics of quantum phase transitions. And essentially, there are a series of quantum annealers that have been made available and are commercialized, in particular those by the companies D-Wave. And presumably you can think of them as programmable simulators of many-body quantum spin systems. And pretty much the whole talk is focused on this work, which is a long collaboration with the group of Hidetoshi Nishimori, who introduced the paradigm of quantum annealing, and the group of Daniel Lieder, who's a leading expert on quantum annealing, and many of the students and collaborators of Nishimori. Sei Suzuki, who's also did very important works on early theory of annealing. And I want to emphasize the work of Fernando, who just moved from my group to that of Juanjo Garcia Ripoll in Madrid. Okay, so let's get started. Yeah, so I just want to essentially touch on 2 ideas. First is going to be a bit of the theoretical setting to describe phase transitions and how, when they are driven in finite time, they give rise to formation of topological defects. And then we will see to what extent we can use quantum annealers to learn about these dynamics of phase transitions in detail. What's the key idea? Well, just think of a ferromagnet at high temperature, above the Curie temperature, the order parameter vanishes. And, if you cool it down in finite time below the critical point, then the order parameter starts to grow. but it does grow differently in different areas. We have a scenario of spontaneous symmetry breaking with a degenerate vacuum manifold, and if nothing tells the system in which way, which ground state to pick, what will happen is that causally separated regions of the system will make independent choices of the broken symmetry, and at the interface of the resulting domains, you will get topological defects, which here in this picture will be domain walls. Yes. And you may wonder how the patterns in the final non-equilibrium state depend on the time scale in which you drive the phase transition from the high symmetry phase to the broken symmetry phase. This is something that was addressed by Tom Kibble and Kibble-Zurek in a series of works in the 70s and 80s. The key prediction of their works is that the typical length scale of the domains in the broken symmetry phase scales universally with the quench time, so the time scale in which you cool the system, following a power law with a power law exponent, which is solely expressed in terms of equilibrium critical exponents. So nu being the correlation length critical exponent, Z being the dynamic critical exponent. And testing this very simple power law has been the series of sustained efforts over the last four decades. I will just try to present how this power law emerges. It's very simple. The key ingredients is you just assume you have a continuous phase transition and look at the divergence of the equilibrium relaxation time and the correlation length as a function of the distance to the critical point, where lambda is the control parameter, has some critical value. You define this dimensional ratio, and essentially you start from these scaling relations. Now, you assume that I'm still having difficulties to swap the slides and but the following thing is you change the parameter lambda as a function of time in such a way that this dimensional ratio, say, can be linearized around the critical point in such a way that it is linear in time times, some time scale, which is the quench time. And the next thing is you use the equilibrium scaling relations kind of in the adiabatic approximation. So you look at what will be the instantaneous value of the equilibrium relaxation time when the dimensionless distance to the critical point is epsilon t. So you just take this power law, you look at the instantaneous value and compare it to the time scale to the time that it takes to reach the critical point. According to this quench, the critical point is reached at time equals 0. So you start at some negative time, and you wonder, when the relaxation time is larger than the time left until you reach the critical point when you are driving the control parameter in this fashion. Well, this matching of time scales, which is very intuitive, allows you to identify a time scale, a characteristic time scale in which the system falls out of equilibrium. That's the so-called freeze-out time. And now you can also then use it to, to estimate what is the associated correlation length. So you take the equilibrium correlation length, you take this freeze-out time, you plug it here, and then you substitute it here, and that's how you end up with the Kibble-Zurek prediction for the scaling of the correlation length of the typical size of the domains in the broken symmetry as a function of the quench time scaling universally. Yeah, so this is a very simple hand-waving derivation, but this is essentially the essence of the Kibble-Zurek mechanism. And how about quantum phase transitions? Because all this was pretty classical. So, there were a series of works in 2005 by Anatoly Polkovnikov, Bogdan Damski, Jacek Jarmaga, Kibble-Zurek, Uwe Dorner, and Peter Zoller, that using as a testbed quasi-free Fermion models, in particular the transverse field Ising model, they established the validity of the Kibble-Zurek mechanism in the quantum domain. How do you do that? Well, essentially, there are well-known techniques to map these spin systems into quasi-free fermions. And if you look at an observable which counts the number of kinks, so of course the Ising Ising model has a ferromagnetic phase with two ground states, doubly degenerate, either all spins up or spins down. And topological defects in this model are misalignments in which you have a spins up and then adjacent spin down configurations. And this kink operator essentially counts the number of interfaces between these domains. And it does have also a very simple representation in the fermionic language, essentially just as the sum of occupation numbers in its model. Well, the dynamics is essentially solvable, exactly solvable. One needs to do small approximations, but when you vary the magnetic field in time from a large value to a small value, so that you go from the paramagnetic phase to the ferromagnetic phase, then you can perform a computation of what's the expectation value of the kink operator in the final non-equilibrium state. And this scales with according to this is given by this expression, which is consistent with the prediction by the Kibble-Zurek mechanism for nu and z equal to 1. So, it's essentially in agreement with the classical Kibble-Zurek mechanism. So this calculation established, there were numerics done, analytical studies, approximate studies, and they all confirm essentially the validity of the Kibble-Zurek mechanism in the quantum domain. What we know today is that the Kibble-Zurek mechanism is broadly applicable. There have been many studies in both integrable and non-integrable systems, and many experiments as well, which are consistent and supporting of the validity of the Kibble-Zurek mechanism. We brought a review in 2014, but there has been substantial progress ever since. In particular, in the last couple of years, some really beautiful works appear. So that was all about the Kibble-Zurek mechanism. I want to present some theory which we also tested in the laboratory, and that goes beyond the scope of the Kibble-Zurek mechanism. And this is something I first proposed in this work in 2018, and there were some experiments, and I will also mention further experiments. And the idea is, you prepare these non-equilibrium states by driving a system across a critical point. And so far, the Kibble-Zurek mechanism was mainly focused on questions such as what's the typical size of the domains, what's the average number of topological defects, what's the density of defects, and so on. But we could as well ask more interesting or more broader questions such as what's the probability distribution that I have a well-defined number of kinks, or what are the fluctuations in the number of kinks of the non-equilibrium state after crossing the phase transition. So this is what we call beyond Kibble-Zurek physics. And it's very simple. Essentially, to demonstrate it in the case of the transverse field Ising model, you take the same model, you take the same observable, but instead of looking at its expectation value, now you look at the full counting statistics of this observable. So you look at the eigenvalue statistics. So this operator has eigenvalues, which are 0, 1, 2, infinity, the number of topological defects, and you define what is the probability that the well-defined number of kinks appear. So the probability that an eigenvalue comes out in a measurement. And I should say, when I did this in 2018, I was at that time, at the time of writing, certainly unaware of earlier efforts by 2007, even though I know perfectly sure that I had read this paper and I cited it before, but somehow I did not cover it. But so there was a pioneering effort by Lucas Chincho and co-workers who did this, and there I was able to provide some further results. So, well, here you see you have this delta function of an operator with some eigenvalues. When you see something like this, it is just a good idea to take the Fourier transform and introduce the characteristic function, because then this will be essentially the trace of the state times the exponential of a Hermitian operator. And in this case, this was a free Fermion model. So this characteristic function takes a very simple form. You can write it down as the product over all the modes in the fermionic space and the fermionic language of, and it takes an exact computation so that this is the structure of the characteristic function. Now, this may look a bit technical, but if you go to a textbook on probability theory or in statistics, you already know by looking at this expression what kind of distribution you have. And this is the distribution in which you have k coins, each of them biased with, say, probability of having head pk, probability of having tails 1 minus pk. And you are asking, what's the cumulative probability of having a given number of heads or tails? Yes. So this is what is called a Poisson binomial distribution. And what is even nicer is that we can estimate what's the probability of getting heads or tails. So kinks or no kinks, or occupying a given fermionic mode or not occupying it, according to the Landau-Senner formula, which sets this probability equal to a Gaussian with respect to the wave vector, or an exponential with respect to the Quent's time. So now this allows us to look at the, let me just skip this slide. So we'll have an exact expression for the characteristic function. By taking its Fourier transform, we then get the eigenvalue statistics of the kink operator, and we can just go ahead and display these exact results here for Ising chain, say of 100 spins, which is driven across the phase transition. And we plot the number of kinks, the probability for the number of kinks versus the kink number when we drive the chain at 3 different rates. So here is very slowly, here is a bit faster. Sorry. So this is very fast, this is fast, and this is more slowly. So here you see that when you drive the chain very quickly, the average kink number is peak at large values, and the distribution is as well very broad. As you approach the adiabatic limit, then the average kink number decreases, and also the fluctuations. And eventually, in the adiabatic limit, you start to have a non-zero fraction of having perfect ground state with no excitations at all. And then, so the distribution is no longer symmetric. The histogram is numerically exact. The solid lines are Gaussian approximations given by this formula, where essentially we are stating that the probability of having a well-defined number of topological defects is a Gaussian peak at the density predicted by the Kibble-Zurek mechanism, with a variance which is linear on the density predicted by the Kibble-Zurek mechanism. So it's a normal distribution, but with this peculiar feature that the variance is proportional to the density. Yes, it's not quite Poissonian because it's proportional, it's not equal. Yeah. So, right. So beautiful. Okay, we'll have a Gaussian plot and a Gaussian fit, which looks very nicely away from the adiabatic limit, and more or less tell us the physics. But imagine I want to really understand in depth what kind of probability distribution do I have here. So the best thing you can do is then to take the logarithm of the Fourier transform of the probability distribution. So this is the cumulant generating function. So again, this is a standard trick in statistics, and you use this. This expansion, this cumulant generating function has a formal expansion that generates cumulants, kappa q. So the first cumulant is the density. So this is the typical observable in Kibble-Zurek. The second cumulant is the variance of the number of kinks. So that will be interesting. The third cumulant matches the third center moment of the distribution. So that will also be interesting. And, in principle, we'll have infinitely many cumulants, which are related to the moments of the distribution. Now, again, for quasi-free Fermi models, one can find this beautiful, it's essentially exact. We just took the continuum limit and used the Landau-Senner formula to write down the cumulant generating function in closed form. And okay, so this is still an integral, so we can simplify it a bit. If we take the limit of slow quenches, so large tau q, then we can actually show that this expression collapses into a very simple one, which tells us that the cumulant generating function is proportional to the density of kinks predicted by the Kibble-Zurek mechanism times something that is a polylog function, what is only depends on the conjugate variable to the kink number. It knows nothing about the state. It knows nothing about the Quent's time or critical exponents. So this is just going to be coefficients. Yes, when we combine this expression with the cumulant expansion, we essentially see that all cumulants will be proportional to the Kibble-Zurek density. And this is the main prediction of this theory beyond the Kibble-Zurek mechanism, is that when we look at the cumulants of the distribution of the number of topological defects after crossing a phase transition, all of them will be proportional to the mean density of kinks predicted by the Kibble-Zurek mechanism. Yeah. So all cumulants are proportional to the mean density. So how, just to see it a bit more closely, if I say before that the first cumulant is equal to the mean number of topological defects, and it matches exactly the prediction of Kibble-Zurek mechanism in this large tau Q approximation. If you look at the variance, second cumulant is the variance, and you see it's proportional to the Kibble-Zurek mean density times a numerical prefactor. You look at the third cumulant, that happens to equal the third center moment. It's also proportional to the Kibble-Zurek density times a different prefactor. So the fact that we have a non-zero third cumulant tells us that the distribution is actually not normal. So before I presented a Gaussian approximation, but there's also a theorem that tells us that there are infinitely many non-zero cumulants, and so the distribution is not normal. As I say, the distribution is Poisson binomial. Okay, and what is it you can do, or what's the prediction here? So far, we can plot the cumulants versus the quench time. As all of them are proportional to the Kibble-Zurek density, all of them should scale universally with the quench time, and actually have the same slope, because the same critical power, the same power law exponent, which is set by the equilibrium critical exponents. So here is the first cumulant. That's the density of kinks, and this is what the Kibble-Zurek mechanism will predict. Now, what is beyond Kibble-Zurek is the idea that the variance and the third center moment also scale universally with the quench time, and follow the same power law, and the coefficients are off. So the prefactors are off, but they are given by the theory I just presented. And of course, having good resolutions of high-order cumulants requires high counting statistics that experimentally can be challenging. But even if you have wonderful experimental resources, you may also find that higher-order cumulants are more sensitive, for instance, to finite size effects near the adiabatic limit for long quench times, or breakdown of the Landau-Zener approximation that we use for fast quench times. And it's interesting that the first and the second cumulant are more or less blind to these deviations, but the third cumulant start to know about them. Yeah? So we also have an understanding of how this comes about. Right. So all what I presented so far was only for the quasi transverse field Ising model, which is integrable, solvable, and you may wonder where this is just specific to this model or something more general. So we have shown in a series of works that this is actually completely generic behavior. So we have done studies in some quantum simulators of this very system, transverse field Ising model. We have also looked at phi-4 theories and classical spin models. We have some tests that I will present in quantum annealers, and we have also done numerical tests in higher dimensional systems, such as strongly coupled superconductors described by holography. And I think we will have an update on that tomorrow in the archive. Right, so as I mentioned, the key prediction is that not just the mean density, but all cumulants of the distribution are proportional to the mean density and will scale universally with the quench time. And this is something we can go ahead and try to test in the laboratory in a given platform. And what we did is to use D-Wave as such test bed for this prediction beyond the Kibble-Zurek mechanism. So I just presented a bit the team. So this is one of the visits I made to Tokyo Tech. So this is Hidetoshi Nishimori with Kazutaka Takahashi and his group. This is Fernando, the postdoc that just moved to Madrid, and Daniel Lieder. And there are many other collaborators. I couldn't get the picture from all of them. I want to say that we were not the first people trying to test the Kibble-Zurek mechanism in a quantum annealer. There was actually a first work by Wojciech Zurek, Mike Swolak, Jacek Jarmaga, Bartolome Gardas, using an early machine. These machines are getting updated, so there's like generation of machines, and the first ones were relatively noisy. So there was, when they tried to do it in just a few years back, 4 years ago, the conclusion is, well, we see some trends of the kink density with the rate, but we cannot match them to Kibble-Zurek mechanism. So this early effort was inconclusive. There was no support of the Kibble-Zurek mechanism in this study. More recently, there was work pushed by BU people who embedded the two-dimensional transverse field Ising model in a more recent D-Web machine, which you can take as a better simulator of many-body spin systems. And they saw a crossover between something that matches Kibble-Zurek behavior with something in which the slower you go. So here they plotted versus the velocity at which you cross the phase transition. So this is very fast, this is very slow. And here they have the counterintuitive thing that the slower you go, the more excitations you have. So this is clearly against the intuition from adiabatic theorem, but it will tell you that you have some sources of the coherence and some sources of heating into the system, that the longer you go, the more time they have to heat up the system. Other than that, in principle, the system size was fairly limited, but these are square lattices, some of them very, very small, other ones are more interesting, size of 20. And the agreement, so this they embedded two-dimensional transverse field quantum Ising model that whose equilibrium properties you can describe in terms of the three-dimensional classical Ising model. And there was a reasonable match of the critical exponents with the Kibble-Zurek prediction. I think there may be some update in the theoretical understanding of this model from the group in Krakow. Now, I mentioned, there was this heating they observed, and this is something we already predicted in 2016. If your control field, say in your the magnetic field that you use to drive the transition in a ferromagnet, is not smooth but has fluctuations, then you can show that essentially this will heat up the system. And when you try to look at the number of kinks or number of excitations or the energy of the final state, you do see versus the quench time, here the labels are cut, you will see that, you not just get the Kibble-Zurek prediction, this will be in the absence of noise, but as you crank up the amplitude of the noise, you start to see deviations of the noise, and the slower you go, the higher the number of excitations. This is just heating that we predicted with Anir Bandut and Armin Ramani in 2016. Now, okay, so let's go back to what, this was a bit of background of what previous efforts on trying to test and understand critical dynamics in a quantum annealer. So let's go back to what we did. Yeah. So we embedded not the two-dimensional, but the one-dimensional transverse field Ising model. So essentially the simplest model you can think of. Yeah. So, and in just some peculiarities of this simulator, when you change the magnetic field, you also change the ferromagnetic interaction, ferromagnetic or anti-ferromagnetic, depending on the sign. But it is not possible to tune this A and B independently. And these are the kind of schedules that you can engineer. We use two different simulators. One is located at NASA. The other one is a slightly better model located at Burnaby in Canada. And we collected data for embedding the transverse field Ising model and driving the phase transition from the paramagnet to the ferromagnet in both. There are some peculiarities as to how you have to embed this. The simulators do have a given topology and connectivity of the spins, and described by the so-called chimera graph. And what we did is essentially to try to gauge away any effect of potential errors of faulty qubits. So we embed a chain in 200 different ways in this connectivity matrix of the system. Yeah. For each embedding, for each of the 200 embeddings, we run 1,000 quants and collect the statistics. Yes. So ultimately, we did 200,000 realizations for every quench time. So we have unusually high statistics, which will be very, very hard to attain in other experiments, in other physical platforms. Then we also explore some error cancellations. Let me not go into that. And also to try to make sure that we were not sensitive to fabrication errors of the machine. So we considered both ferromagnetic and anti-ferromagnetic coupling. And following the prescriptions, there's kind of a manual of how to minimize the possible errors in the machine. We also did some random flippings of some spins. Ultimately, we just decided to focus on the anti-ferromagnetic case. We were able to prove up to 4 orders of magnitude of the 3 orders, sorry, of the annealing time, which is pretty good, something you could not do in many other physical platforms like trapped ions or cold atoms. But here you can. At any rate, again, it's known that there are sources of the coherence and 1 over F noise that occurs at long annealing times. So we throw away this data and we look only at this data. Yeah. So this is again from the characterization of the machine. It is already known that this data is noisy, though even though it looks more or less the trends, it looks to it follows the trends, but we just cut it here essentially. So with this, we focus on the anti-ferromagnetic case, and now we collect data in both machines at NASA and Burnaby. We did it for different system sizes of 50 to 800 spins, quenching up to 100 microseconds, and find something that look like power laws. All of them kind of following the same power law exponent, as long as the system size is reasonably large. For small system sizes, we see a different behavior, and we did throw away this data because we think it's just, again, more sensitive to sources of the coherence and fabrication errors in the machine, while the longer machine happen to have a more robust behavior. However, when we try to see where the data collected is consistent with the Kibble-Zurek mechanism, well, we try to fit power laws with the quench time and extract what will be the power law exponent. And what we see in one of the machines is values close to 0.2, in the other one close to 0.3. Now, this is for the transverse field Ising model, where the analytical prediction shows, says that it should be 1/2 the exponent. So in both cases, we have very strong deviations from the prediction for an isolated system. It's clearly inconsistent with this data with that of a isolated transverse field Ising model. So now comes a bit the art of trying to guess, what is the right physics at hand. And right, so I can just put here a map with the possible values of the power law exponent in a Kibble-Zurek kind of plot. For the density of kinks, scaling with the quench time. If I plot the values, the theory will tell us it's a value of 1/2. One of the machines has a value of 0.2, the other one has 0.3. And, we try to see where this is consistent with classical theory, so-called spin vector Monte Carlo model, essentially just classical rotors with Monte Carlo updates. And this is, the behavior in the machine is clearly distinct from the simulations there. And what we were able to do is to come out with a description in terms of a quantum open system that folds and covers the regime, not just this value, but actually covers the regime of critical exponents shown by the data collected in the D-Wave machines. From that point of view, this will suggest that this is the first testbed of Kibble-Zurek mechanism in a many-body open quantum system. Yeah. As such, I would say this is a milestone, because if you follow the literature of Kibble-Zurek mechanism, there has been no other test that I know of probing Kibble-Zurek in an open quantum system. So this will be the first one. I just want to put a caveat. We also came out with a classical model, which is able to account for part of the behavior, and we will see how this unfolds in the rest of the talk. Now, what's the quantum model of open Ising chain that we use? It's just a standard spin boson model in which you have the Ising chain, and each of the spins sees a set of harmonic oscillators to which it couples via this kind of bilinear coupling, where the sigma set component of the spin couples to to essentially the position of the oscillator. You have these independent oscillators, and for simplicity, we assume that we have an ohmic spectrum with a sharp cutoff at a given frequency, and we have a coupling constant eta. Yeah? And okay, so the motivation for this is first, this has already been shown to be a useful model in the context of quantum annealing, but it is also interesting that both ground state quantum Monte Carlo calculations and studies based on renormalization group show that this kind of coupling of the Ising chain to with a spin boson coupling does not kill the phase transition, but simply renormalizes the critical exponents. So in the isolated Ising chain, we have correlation length critical exponent being 1, dynamic critical critical exponent being 1. And the effect of this coupling has been shown before to just vary the value of nu and value the value of z. On top of that, we did extensive numerics based on time-evolving decimation block. There's a typo here with quasi-adiabatic path integral method, and this allow us to prove the effect of the temperature. We essentially just focus on the zero temperature case. And what is interesting is that this model, when I plot the density of kinks versus the annealing time, by varying the spectral function, in particular the coupling constant theta, I can tune this power law exponent. So this is our, of course, numerical simulations. We do a power law fit, and if we extract an exponent, we see that essentially we are able to tune the effect of the power law. Yeah. So that's what gives this theoretical model of an Ising chain embedded in a bath of harmonic oscillators the flexibility to account for the data collected in the D-wave machines. So essentially, with this theoretical model, we are able to cover a pretty large set of power law exponents that approach all the way to the isolated case, but are also in the range of the observed values. So this will suggest that effectively, what we have is an open quantum Ising chain. This is completely natural given the kind of implementation we have, but this is still interesting to know where the behavior is can be described in terms of a classical model. Yeah. So the first attempt we did is to consider the spin vector Monte Carlo model, in which each spin is replaced by a rotor. So its quantum spin is replaced by a classical rotor. And we fake or mimic the paramagnetic term, the magnetic field, with a term which goes with sine of the angle of its rotor, and the ferromagnetic interactions with the cosine of the theta. Yeah. So this is based on early studies. This was proposed as a classical benchmark that could rule out quantum behavior, at least could provide an alternative explanation of the phenomenon. Yeah. And when we did it, essentially, we did numerics based on this spin vector Monte Carlo, which, by the way, has the issue that you have to do Monte Carlo updates and you want to describe real-time dynamics, but there's ambiguity as to how you choose the rule for the update and how do you define the time step. But essentially, the power laws that appear are inconsistent with the ones observed in the D-wave data. So it's not that we can describe D-wave data with this model. Yeah. So this was the first attempt to explain the behavior with a classical model. Failed. We tried this. This is a standard kind of a state-of-the-art benchmark for quantum annealers, where you try to use a classical model to account for the behavior, and this one didn't cut it. Yeah? So after we published the work, I continue working on this with Daniel Alonso and Antonia Ruiz in Tenerife, Fernando, who I mentioned before, David Subires, who was a master student in Bilbao at the IPC. And what we consider is something very simple. We still use a model of classical rotors, but now rather than look than using Monte Carlo updates, we consider Langevin dynamics, where each of the rotors has an inertia term, a damping term, and is subject to noise. Yeah? So this has lots of advantages with respect to the spin vector Monte Carlo model. By construction, it's expected to fulfill fluctuation dissipation theorems. So it's a nice model that thermalizes to a given temperature, but very importantly, introduces a tunable dissipation scale, a dissipation strength gamma, that has the potential to actually tune the power law exponent. Essentially, what I can say is that the standard benchmark used in the community, it is just too restrictive. It's a bit puzzling that people have not tried to push and develop better classical benchmarks, because by construction, this one is very limited. So there's no dissipation time scale here that may allow to mimic, you can have classical dissipative systems that also fulfill Kibble-Zurek mechanism, but by construction, this benchmark will never be able to capture them. The one we propose does have this potential, and what I can show you here is, so this is just classical Langevin dynamics simulations that we did, Fernando did, and David, the first two authors, and you see a power law scaling of the density of kinks, beautiful match with kind of Kibble-Zurek power law predictions. We perfectly understand the emergence of different critical exponents in the overdamp and underdamp regime. This is actually understood since, I would say, 20 years ago, based on works by Laguna and Zurek. And that's why we proposed this model, because we knew that it will sum up, it will broaden the kind of phenomenology that is consistent with classical behavior. Indeed, when you plot the kind of power law exponents in the scaling of the density of kinks with the annealing time as a function of the dissipation strength, we see that we can cover a wide range. Yes, and actually this wide range is actually in the regime of the data collected in the D-Wave machines. In particular, the NASA machine seems to be very noisy. It's not something we can describe, but it's consistent with the, it reproduces the same behavior that can be captured by the spin boson model, and it does reproduce the behavior seen in the Burnaby machine, which is the low noise machine. So the claim that this was a simulation of a Kibble-Zurek mechanism in a quantum open system, this is possibly true, but one should keep in mind that there's also a classical model that can account for this behavior. What there is no doubt is that this is a test of Kibble-Zurek mechanism in a many-body dissipative system. Yes, still quantum, of course, but yeah, where the behavior is exclusively quantum or not, it's what we are discussing. Now, that was all regarding Kibble-Zurek part. Now let's go a bit to what lies beyond. And is this possibility of probing actually the distribution of the number of kinks. This is something that we did, and these are the histograms for different annealing times using D-Wave data. And we can see a beautiful match with the theoretical prediction in which the kink number distribution can be well approximated, as we saw before, by a normal distribution in which the mean scales with the Kibble-Zurek prediction and the variance scale is proportional to the mean. This should be a kappa 1, not a kappa 2. So the variance is proportional to the mean. So this is, I think this was, so we had an earlier experiment in trapped ions, but this is the first test of physics beyond Kibble-Zurek mechanism, in the sense of probing the fluctuations of the number of topological defects in a many-body simulator. Yeah, so where classical quantum open or isolated, this is the first test of in a many-body simulator. There have been a few beautiful ones more recently, but I just want to emphasize this feature. Now, a prediction of the theory is not, we'll have these Gaussian plots, but as we saw before, is that the cumulants all follow the same power law scaling with the annealing time, and this is again D-Wave data. This is not numerics, and you see beautiful power laws, all the scaling with the same slope in agreement with the theory. Now the theory was for an isolated system, and the behavior in the machine is clearly governed by dissipation, and yet we have the same kind of physics in which all cumulants are proportional to the mean. The only thing that happens is that the scaling of the mean, it is modified by dissipation, but the ratio of the cumulants remains unchanged. And this is something we did check. If you take say the variance of the number of kinks with respect to the mean, then you see that it is yes, a straight line independent of the quench time, and the value is consistent with the theoretical prediction for an isolated system. So the only thing that dissipation is doing is to alter the behavior of the density of kinks. Is not altering the shape of the distribution. And this is again consistent with the theoretical model that we have. And again, I want to emphasize, this is D-Wave data, but we can do the same thing with the new benchmark, which is the spin vector Langevin model, essentially classical rotors evolving under Langevin dynamics. And you also see that you get the same kind of constant ratio of cumulants. Each of the cumulants scales universally with the annealing time, but the ratio of any two cumulants is a constant, pretty robust and pretty annealing. And now this is a classical simulation, which again is able to capture the same kind of physics. So by this comparison with classical and quantum models, I'm also emphasizing that this specific experiment has no signatures of anything we can call quantum advantage, because the behavior, even if it's quantum, can be reproduced by a classical model. What is important, from the point of view of foundations of non-equilibrium and statistical mechanics, is that we saw that we have a universal distribution of the number of kinks, which is a Poisson binomial distribution, and we have provided the first test of this kind of physics in a simulator of many particles. And I guess I'm already closing, but essentially, this the update is progress is quite fascinating. So this is just a preprint that appeared last week. It was announced earlier on through a talk, but this is finally the preprint, in which they have reproduced essentially the same kind of analysis that we did. So this is essentially the group of D-Wave with some of the common collaborators, Daniel Lidar and Nishimori, and many others. And they went to the regime of very fast sequences, where you expect any source of the coherence to be, suppressed. And they did see a behavior which is fully consistent with that of the isolated transverse field model. So, our data was in this range of 0.2, 0.3, but now the last experiments, which was for very fast sequences, they did see beautiful power laws for the density of kinks, the variance, the third cumulant. In agreement with the theory I did in 2018, they also collected, the full counting statistics. But now, what is interesting is that the behavior of the scaling is that of an isolated descent chain. So this shows essentially, how the engineering of these machines is progressing to create better and better simulators with lower and lower noise, but also how the simulators can be used to probe fundamental physics in non-equilibrium statistical mechanics, where we have seen, the first test of Kibble-Zurek in an open simulator, the first test of Kibble-Zurek, or physics beyond Kibble-Zurek in both an open simulator and an isolated simulator. Yeah. So from the point of view of fundamental physics, I think this is very competitive with respect to any other experiments. I could, this is something we could discuss at length, and it's the subject of IFIMAC talk, the comparison with other platforms. But this is quite a much and fascinating. Okay, so with this, I want to close. I announced the basics of Kibble-Zurek and presented the first test in an open system. The physics beyond in an isolated system in this recent preprint of last week. I'm not co-author of that, but our work was essentially dissipative. And in the as a byproduct, we also introduced a classical benchmark which makes much harder to rule out classical behavior, and can capture much of what is in many of the previous experiments. So with this, I just close, and I want to thank you all for your attention.
Thanks a lot, Adolfo, for your very nice talk and this insight to lattice model and the use of quantum simulators. I open the talk for discussion. Are there any questions? So let me start with one about, you mentioned that it's not quantum supremacy because you simulated essentially a classical model, but how, say, if you have the simulation, you probably have not as large systems as in the simulator. So how is the ratio between what you can do theoretically on the computer for simulation and what they can simulate on the D-Wave, for example?
Yeah. Okay. So So I guess by quantum supremacy, I understand that you have a quantum system that can perform a task that cannot be reproduced by a classical model. Yeah. So I do believe that the web machine is, of course, it's ultimately quantum, where the behavior that was observed to what extent the behavior can be reproduced by a classical system or not is one of the points I address. And the early results of using the standard benchmark in the community will suggest that no classical model could reproduce it, but we introduced this new benchmark, spin vector Langevin model, that can indeed account for the observed behavior. Yeah, this is not to say that the machine is classical. It is that the same phenomenology can be reproduced by a classical model. So from that point of view, this rules out any signature of quantum supremacy in this experiment, which was essentially not an experiment designed as an experiment to exhibit quantum supremacy or a strong, perform an important computational task. It was mainly designed to probe a paradigm of non-equilibrium statistical mechanics, the Kibble-Zurek mechanism, and so on. Yeah, so this is answering part of the question. The rest is, what are the system sizes used? So in the machine, the number of qubits that can be used keeps increasing. The recent preprint, we use up to 2,000. Yeah, our simulation, our earlier data was for up to 800 spins, and if you think they are open and you want to simulate the spin, spin boson model for 800 spins, I don't think you can really do it. I think, of course, this is, you can push numerics, you can push approximations, but there's of course no exact simulation that you can do of such a system. Yes. So in some sense, you also see it's not a non-trivial. It's a non-trivial scenario that you cannot. The isolated Ising chain. This is solved with pen and paper. So doesn't matter the system size. The moment it is open, it becomes like a strong computational task. So I present numerics, which was done by, if I'm not mistaken, Sei Suzuki. I was not involved in that part, based on the spin boson model, which used the time evolving block decimation algorithm with another paradigm, which is that of the quasi-adiabatic path integral method. These are all approximate numerical techniques. And you can also criticize them very strongly in some sense. Yes, they range of tunability of the quench times, the limitations on the kind of system, the boundary conditions you have to put, and so on. There were many. It's the best we could do, but it is not a nice, clean comparison with experimental conditions. The experience can clearly go beyond what can be done. Yeah.
And since you mentioned the spin boson model, you choose a particular coupling to the C component of the spins, which essentially means that you have pure dephasing between, say, of the spin of the two spin states up and down. How sensitive, or say, if you would introduce spin flips, or say,
the kind of dissipation mechanism. Oh, sorry. Yes.
Would that change much if I would couple to other spin degrees of freedom?
It will. Yes. So this is crucial. There are some studies that have already shown it. In particular, one of them was from my group in Boston. One of the things you can see is this. This is essentially a dephasing mechanism where you induce heating. Yes. One of the things you can do is, one of the things you can see is that you preserve the phase transition without changing the critical exponents, but then you have a heating source. So this is what we saw in this very simple model, where essentially it was just fluctuations in the magnetic field. The other thing you can do is, if you have this kind of spin boson models, and now you don't couple to the sigma z, but you couple to sigma x or something like this, you can also destroy the phase transition. So what we saw is that the phase transition was preserved with renormalized critical exponents. But this is specific to the kind of coupling we have seen. It's also the kind of coupling we think there is, and we have provided compelling evidence that this is, in close agreement with the data collected in the machines. But if we were to change this coupling, we can see qualitatively different behavior, inconsistent with the one we have in the machine, but that may be interesting to study, and some people have studied.
More questions? So I would have a last one about time of the transition. Say if you come from you go from, say, I think it was the anti-ferromagnetic phase to the ferromagnetic one. Would it be the same if you go the other way?
Oh, you mean if you go from the broken symmetry phase to the high symmetry phase? So people have studied these reverse quenches. And there are some also applications in the context of annealing where you just not anneal like this, but you do like you go back a bit and you pump a bit of energy and you have to anneal back and so on. Like no, I think it changes qualitatively. Yes, certainly the understanding based on Kibble-Zurek changes. Yes, because what the essence of Kibble-Zurek is that when you drive a phase transition from a high symmetry phase to a low symmetry phase, there are different ground states that can be chosen. And it's locality in this breaking of symmetry that the spatially separated regions of the system can make different choices of the ground state manifold, of the broken symmetry, is what gives rise to the topological defects. Now, if we go from the broken symmetry to the high symmetry phase, there the order parameter vanishes. So pretty much, like I guess, the key reasoning breaks. You may still be able to find even some power law scalings consistent, where you see number of excitations scaling nicely with the quench time. But this will be more in the standard setting of finite size scaling. I guess you can go into the difference between Kibble-Zurek and the standard finite time scaling.
Okay, thank you. I see no further questions, so let's close with the announcement that next week we will have a talk by Natalia Ares, also about quantum technologies, or a topic in that field. And so let's close the official part. If anybody would like to stay and chat a bit with Adolfo, he's welcome to do so. But yeah, so thanks everybody for attending, and see you. Bye.
Thank you very much. Cheers.